They looked all professional and everything. Obviously not coming here. All right. Let's start where we left off. I know I left you with a cliffhanger. You know, basically, well, it's actually an incline hanger. All right. I think we had a 5 kilogram force, and let's just kind of start over on it a little bit. And it's attached because remember what I said. And then we're going to get to Sir Mix-a-Lot here. We're going to get friction on here in a minute. So we got this, got this. Somebody tried to play Stump the Chump with me today in the afternoon class, and it worked pretty well. And anyway, we're going to AV fight. Are we okay? Okay, we're good. All right. I thought the AV crew was going to start duking it out back there. All right. But anyway, somebody asked me they tried to play Stump the Chump here, and they said, hey, how do we know that this tension is the same? And I was like, because it is. It just is. Don't worry about it. But that's a very unsatisfactory answer. But the actual answer is Newton's third law. Because this guy is pulling on this guy, so we have what? An equal and opposite reaction, so that's why the two tensions are the same. Okay? All right. And the guy who asked the question actually came up with the answer. He goes, isn't it Newton's third law? And I went, yes. Glad you thought of that. I held off, you know, because I knew the answer. I'd forgotten. Anyway, all right, so here's where we left off. Now, remember what we did. We're going to make this guy flat. All right, because here's what we do. Is you look at the thing, here's the steps you go through. Here's the steps you go through and know how to do this because I'm going to give you a frictionless. I used to put friction on something like this, and that was just too ugly. But so I'm going to give you a frictionless thing a lot like this, okay? And you're going to have to figure it out, all right? And it might be the same thing, but I'm going to change. What if I put the 5 kilogram, the 1.5 kilogram here? This is going to go different directions, all right? But anyway, for right now, we're going to assume that the 5 kilogram is going to pull it this way. So you look at the whole thing and you go, oh, I've got an acceleration going this way. So if this block is accelerating this way, what's this block doing? Accelerating up. He's got to be accelerating up. Okay? And I think, for those of you who pointed down, I think you were getting confused with he's 1.5 G going down. That's what's pulling it the other way. Otherwise, the whole thing would just be careening down this way. Now, here's what you do. You take each block. Now, there is a way to do it where you take all the blocks and you just set them in a straight line like a train, but I don't like doing that. The other thing that does is that cancels out your tensions and you get an acceleration. Then you have to go back to your individual systems to find the tension anyway. So let's take each block. So what you do is you look at each block and you look at the forces working on that one. And then you take this block and you look at the forces working on that. Let's take this one first. Because here's the question that they're going to ask. What is the tension? What is T? What is A? What's the acceleration? That'll be, I'll tell you right now, it'll be question number 1 on the test. Look at the diagram below. Find the tension and the acceleration of the system. Okay? It's a simple question. It'll be worth 20 points. So here, and you'll go, I know how to do this. I'm going to take a look at this first thing and go, okay, some of the forces, I'm going to draw my free body diagram of the first one. It's got a tension going up. It's got mg going down. So I'm looking at the 1.5 kilogram guy, okay? And I'll say, okay, and he's got an acceleration going up this way. I'm making that assumption. Now, when I get all said and done, if I get an answer that says A equals negative 0.5 something, or whatever it happens to be, if A equals negative, guess what that tells me? I've got it going the wrong way. But everything else is fine. Just don't give me a negative A on your thing. It's going to be A equals some positive number. All right? So, here we go. So let's erase this. So we look at this guy and we go, okay, I just want you to get into this habit. Some of the forces in the x direction equal, what's going on here in the x direction? It's kind of a trick question, but not really. Nothing. Zero. Nada. So some of the forces in the x direction is 0, and there's this nothing on that side of the equation either. Now, some of the forces in the y direction equals 1.5a, equals this guy, times the mass, which is 1.5. That's the first thing. Now we look at the forces. We go, okay, I know it's accelerating up. I said it's accelerating up. I don't know what the acceleration is, but it's 1.5 g. It's a 1.5 kilogram mass, and this will equal, it's going to equal, come on in. It's going to equal, oh, you didn't go, oh, okay. So, I thought Molly was already here. That was Molly, by the way, in case y'all don't know. Okay, now everybody knows. And everyone in TV land knows. Okay, we got T minus 1.5 G. Okay? There we go. And we'll go, oh, I need to find T and I need to find A. I can't do it because I only have one equation. I got two unknowns. So I'll go to my next thing. Let's look at the 5 kilogram block. Now this one, remember what we did. We made him flat, we rotated him flat, and then that gravity vector, the 5g vector of his weight, now goes this way. Okay? It's now cattywampus because he's got a g vector going like this, a g vector going straight down like this, and then these two guys is what we're going to do. He's got a normal vector going up like this, normal force. All right, so now, well, we know he's got a normal. He's pushing up with a normal force going this way. There's a normal force of the table, the incline pushing him up that way. And since I've got a vector that's cattywampus, what do I do with all cattywampus vectors? Break them into components. Okay? So, going down, coming back across. And that's our 90 degrees. Now, what's this angle right here? What? What's that angle? It's going to be 20 degrees. We could go through a Miss Crunchmeister geometric proof of similar triangles, but I'm not going to. I'm just going to tell you. Just get into the habit that when you see this incline here, and you draw your cattywampus weight vector like this, that's that angle. It's 20 degrees. Now, one of the bad things that I did was I've kind of beat into your head that cosine goes with the x-axis and sine goes with the y-axis. Not this time. You got to remember, cosine is for the adjacent leg to the triangle, all right? And sine goes with the opposite leg. So the adjacent leg to this angle is this guy right here. So he gets cosine. The opposite leg is this angle, so he gets the sine. Okay? All right, some of you that have had trig go, oh yeah, but there's quite a few in here that never had trig, so I just wanted to make sure that you knew as soon as you get one of these things, make it flat and go, okay, this will be 5g cosine of 20, and this will be 5g sine of 20. That's the first thing you do with an inclined guy. All right? And then the second thing we do, once we get those in place, we go, okay, I'm going to take this vector and put him right here. Here's 5g sine of 20, and here's my tension coming this way, T. And there's all my forces acting on this guy. Okay? There's all my forces acting. So I moved him from here up to here. Now, do I have to worry about this 5g force anymore? I don't, because I got rid of him because I broke it down into the two components that are now easy to work with. I can stick them into fx and fy equations. That's why I did that. Okay? All right. So now let's take the sum of the forces in the x direction. Sum of the forces in the x direction. Oh, I forgot one other thing. Remember, he's accelerating this way. So the first thing I'll write down is negative 5a. Because this a and this a are the same thing. So that's the first thing I write down is, okay, Newton's second law. The sum of the net force in the x direction equals 5a. Is making it go 5 times the mass times that acceleration a, which I don't know yet. Okay? And that will equal, we just look at these two guys. Oh, here's my only 2. That's t minus 5g times the sine of theta. Now, sine of 20. Now, here's the other thing that I found out in rehearsal this afternoon with the other class is when we get done, I'm going to disregard the negative signs on gravity because I've already taken care of it. I've already factored it out here. Okay? I could have made this plus 5 times and put the negative g in there, but that gets too ugly. So I just factored him out. I made it minus 5g. Because he's going in, because this g is negative, that's why he's going this way. So I just subtract his magnitude like that. Okay, now I've got something to play with. I can go, oh, I can find t and stick it in here. Oh, but first let's take a look at the forces in the y direction, just to get used to something here. Actually, I want to put him above, kind of like I did here, because this will come in handy when we get to friction. So I'm going to take the sum of the forces in the y direction. Now, is this guy accelerating up or down? Is he crashing through the incline? No. Is he flying up in the air? No. So he has an acceleration of 0 in the y direction, right? So I just go, all right, 0. But I'll go ahead. It'll help us later on when we get to friction to go, oh, well, he's got a normal force. And here's the deal on a normal force. When I push down perpendicular to the surface, it's what's pushing back up perpendicular to the surface. Okay? So if I push on this guy, the normal force is going that way. When I push on this guy, the normal force is going straight up. If I push at an angle, like this guy, the normal force is perpendicular to the surface. All right? But now, since I've laid him flat, he's just coming straight up, minus mg cosine of 20. Oh, let's put the 5 in there. 5g cosine of 20. And so I could go ahead and solve it and say the normal force equals 5g cosine of 20 if I wanted, but it's not going that f of y is not going to help me to solve this problem. But what is going to help me is, let's add 1.5g to both sides and get t over here. So I've got 1.5a plus 1.5g equals t. Aha! I'm going to take him and put him right there. So I'm substituting this guy. I'm going to plop him in for that guy. I get minus 5a equals 1.5a plus 1.5g minus 5g sine of 20. There we go. Ha ha! I have one equation and one unknown. We did it. We're awesome. Way cool. Let's go ahead and finish. So here's what we're going to do. We're going to take minus 5a. We're going to subtract 1.5a from both sides. So we get minus 1.5a. See, so this goes to 0. Equals 1.5g minus 5g sine of 20. All right. Now this comes out to be minus 6.5a. And this actually comes out to be like a negative 3.4 or something like that. Hold on a second. Negative 2.1. It's actually in newtons because I got a mass times an acceleration, so that'd be negative 2. Hey, this is going to work out great because when I divide the negative 6.5 by the negative 2.1, what do I get? Positive a, and a positive on both sides. And so we guessed right and go in the right direction. So let's divide this by negative 6.5, divided by negative 6.5, and I wind up with a equals positive 0.32 meters per second squared. Ta-da! Now, we found a. We can find the acceleration now, or the tension, pretty quick. We can just, okay, so for tension, since I said over here t equals this, or I could just put the a back in here and solve for t here, if I wanted to. It doesn't matter. You just take this a, stick it in somewhere, let's put it in here, equals 1.5 times 0.32 plus 1.5 g. And to be honest, I forgot to figure out what that was. So it's about 0.45 plus 14. It's about 15.5 newtons or something like around 15 or 16 newtons. Eric, do you have it? Oh, okay. All right. Yes.
For the G that's on the top part, you said you already took it out with the negative in front of the 5, right?
Yes.
So when you put that in, you just put in a regular 9.8.
Wait, right here? Yeah, because he's already been taken care of because I made him negative over here also. And so now when I break, so now he's just a magnitude. I've taken care of the direction here. So I'm just dealing with the magnitudes from here on out. All right? Makes it much easier than carrying that negative 9, then going plus 1.5 times negative 9.8 and carrying it all the way through. Okay? It's kind of a, you know, it's kind of a trust the force type thing. You know, in other words, once you factored him out, let it go. Make it just use the magnitudes. He's all positive now. It's all good. Okay? Trust the algebra. Okay. So this might be one of those that looks, oh yeah, that was easy when you did it in class. Now when I assign you one, don't panic. Just break it down step by step. All right? You look at this guy, find the equation, and when you look at one of them, you'll find the equation for one thing and you'll substitute it in for the other. Works every time, without fail. All right, let's talk about friction, okay, which friction is a good thing. It's actually what's helping me walk across back and forth, keeping Team Yi busy, following me with the camera. Okay? All right. So let's talk about friction. Let's not forget about the normal force either. There's 3 types of friction. Okay? There's 3 types. How many of you have ever worked in an office or been helping somebody clean out their basement and you've had to move a filing cabinet without a dolly? Of course, our City Hall employees had to move lots of filing cabinets. Okay? Yeah, move these records. We have no idea why we kept them or why they're still over there. All right. Well, when you do that, or you've everyone's tried to scoot something heavy, right? That didn't have wheels. All right. Now, friction is basically 2 surfaces, they adhere together. Okay? And it's electromagnetic forces, actually, that are causing it. And there's no such thing as a perfectly smooth surface. If you get down at the microscopic level, subatomic level at this whiteboard, feels nice and smooth. If I was a little electron on this thing, I'd be going, wow, look at all these peaks and valleys at different energy levels and everything else. I mean, it'd just be a mess. It'd look like Nepal, okay? And so those things is what, that adhesion is what causes friction, all right? Now, if you've ever tried to scoot something without wheels that's heavy, oh, like this thing. Perfect example. Let me get it out here. Oh, let's leave that door closed anyway. Now I got you. All right, now, okay. Now, when I start to pull on this, it's pushing back. When it's not moving, the force that's keeping, okay, I'm pushing this way. What's the sum of the forces on this thing? What's the net forces on it? The sum of them? Zero, because it's not moving. So what's acting back? What's pushing back? The friction on the floor is pushing that way. That is static friction because it's not moving. Okay? And static friction looks like this. The symbol for static friction looks like this. Static friction. Okay? It's F of S. And F of S equals this. Static friction equals mu of S, that's the small Greek letter mu, times the normal. That's why I wanted to have all that normal stuff up here so we can look at some sliding blocks and things. Okay? So that's mu of S is the normal. Now, start pulling on this thing. Now, all of a sudden, ooh, it gave. And then it starts sliding pretty easy. All right, now, what is the net force on this thing? It's going this way, right? All right, so that is kinetic friction. And that looks like F of K that's kinetic friction. And things look like this. You apply a force, you start applying a force, you apply a force, here's your static friction. Apply it, boom, here's your force that you're applying, then all of a sudden, bang, then you get kinetic friction right here, and you don't need as much force. Okay? You don't need quite as much force. And kinetic friction equals mu of K times N. And these mu's, mu of S and mu of K, are what is known as the coefficients of friction. Now, different materials have different coefficients of friction. Okay? There's some in your book, and they kind of make sense to you when you hear about them, when you hear them, because you'll be like, this is your force, this is your F of S max, this is your this is your maximum static friction, and then your F of K stays nice and normal, or nice and constant. But anyway, like aluminum on aluminum, okay? The static friction is 1.9, and the kinetic friction is 1.4. Usually, that's unusual. Isn't that how? Isn't that unusual to have kinetic friction greater than 1? Maybe. Okay. What do you think about that? Look, there's your thesis. Materials with kinetic friction greater than 1. Figured it out. All right. Anyway, but like, let's take Teflon. Teflon on Teflon. The static friction is only 0.04. Very low friction. Okay? Whereas the kinetic friction is also 0.04. In other words, you're going to be given these. And if you're not given them, if those aren't given, you will be given this, and you'll be given this, and you'll be asked to find what that is. In fact, they're all found by experiment, by doing things like this. Okay? Okay, so usually the kinetic friction almost always the kinetic friction is a lot less than the static friction, because you kind of break a barrier and then it requires less force. All right, so that's good. So let's do a problem. Oh, and then the last kind of friction, F of R, or I don't know what it is, but it's rolling friction. And if you want to find out about that, take Physics 510, Advanced Mechanics, and they'll tell you all about rolling friction, because it's too hard. I don't know about it. I just know that things roll, and then eventually they come to a stop. Okay. But the reason things roll is because we do have a little bit of friction. We've got torque, and actually, this thing actually deforms a little bit. Okay, and that's why it actually stops rolling eventually. It'll eventually slow down and stop rolling because it's actually got some deformity. There's also sloshing around of the ink in there that are working against it and everything else. But it's actually caused things roll because of torque on the top, and then they start to roll, and then eventually they come to a stop. That's why if you take a ball bearing on a steel surface, it'll roll for a long, long time because there's very little. In other words, a ball bearing on a steel surface has a very small contact area. Okay? But a tire on a road has, it's actually kind of like that. It actually smushes down, right? So it's got a bigger contact area. Yes? Question? Oh, no. Okay. All right. Okay. So that's rolling friction. We won't deal with it too much. When we get to rotational things, we'll deal with it some, but not. We won't try and solve problems with it. Okay.
There also affects the stopping force required to
Yes.
stop the bearing. It's got such a small.
Right. Right. And it's also why. Well, actually, due to static friction and kinetic friction, along with rolling friction, that dragster tires are big, slick things. Why? Because they need the most surface area applied to the ground so that when they apply that torque, they've got the most surface area applying the power to the ground to propel them forward. Okay? And that's why racing cars have slick tires also, so that they can get the most power applied to the ground to get them around the track. But it's also why it's very, very dangerous if it even starts to mist during a race, because they don't have tread. Now we have tread so that we can channel the water, and so we don't have hydroplaning. Okay, but a race car with no tread is going to hydroplane almost instantly. As soon as there's any kind of film of water there whatsoever, it'll hydroplane. So that's why the yellow flag or the red flag comes out as soon as there's a drop of rain. And that's all I know about NASCAR. Or Indy or any of that kind of stuff. Like I said, I think I made an A.J. Foyt reference a while ago. I don't even know if he's still alive. So, okay. But he was the king of Indy back when I was growing up, when Indy meant something. All right, now, so let's take a look at a friction problem. It's just like what we did. It's just like what we did, except we got another force. We got a frictional force working against us. Now, friction does not always oppose the motion. For 3 years I taught physics. I tell people, friction opposes the motion. It doesn't. You know why? Right here. Friction is actually going, when I put my foot down, what am I doing? I'm pushing that way. But what's happening? Because there's friction on the floor, it's actually pushing me that way. So that's why I can walk this way. Okay, so that's not, actually, the force of friction is going in the direction of the motion. Okay? Okay, let's do this. Let's do a classic problem that would be on a test. Here comes question number 2. So again, if you can do this question, here comes question number 2 on your test. Something like it. Now you still got homework to do. All right. But you can't teach physics without inclined planes and blocks. All right? Now, I'm going to put a block on this thing. Okay? And let's say that that's snow. Do they give me snow here? No, they don't. Idiots. Okay, well, let's say it's wood on wood. Let's say it's well-waxed wood on wood. So that way it doesn't give a creaky sound and people aren't going like this or anything. All right. So this is wood. It's going to slide down this thing. All right? It's going to slide down nicely. And the coefficient, and we're going to make that angle pretty big so that it will slide down. So the coefficient of kinetic friction, we're going to make this angle pretty big so that it does slide. Make it like this. Okay, and we're going to call this a height of 15 meters. It's going to be right up here. And it's going to be 5 kilograms. And this is going to be 70 degrees. And the mu of K for our wood is 0.4. And I'm going to let this thing go. Here's my question. How fast is it going to be going when it hits the bottom? Dun, 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 dun. Now, if I was just going to drop this thing from 15 meters, you guys would know how to do that right away, right? Because you'd be like, oh, well, that's just a free fall problem. I don't know how fast it's going to be because mass has nothing to do with it. But now it does. Let's figure out its final velocity. All right? Now, right away, I've got mg coming down like this. I've got a normal force going up like this. Cattywampus to that. And I've got a frictional force going like this. The force of kinetic friction. And I've got an acceleration coming down this way. I don't know what this is. I'm going to tell you right now. What is this force right here? It's coming down this way. Gravity times what? The mass times, okay, it's going to be 5 times g. I haven't got that much. What's left? What needs to go in there? Nope. Remember from our other diagram? Sine of 70. Now, we jump the gun on it. Now, those are all the forces that are at work so far. Well, we've got 5g here, and then we've got this one here. Okay, so let's draw him flat. This time we're going to rotate him down this way. So let's draw this guy nice and flat. So what we're going to do is we're going to figure out what his constant acceleration is. We'll know his constant acceleration. Because we know an angle and we know the height, we can figure out the hypotenuse. So we can figure out how far he went. So we can find his final velocity. Because his final velocity, we're going to say, okay, well, his final velocity squared is going to equal v naught squared plus 2a times the distance d that he went. And here's the distance d. And I'll show you how to find that distance d here in a minute. This is what we're after, but we got to find this guy first. I got to find the acceleration. So that's why I've got to go to my force diagrams and everything. Now, when we get to chapter 5 and we look at energy things, you're going to find out that even with friction, that there's a much easier way to find the final velocity. Okay, so here we go. Let's take a look at the forces here. Now the first thing we do is we draw this 5 kilogram guy, and we draw a force that looks like this. That's our 5G. And here's why I stumped Robin. Because she's like, well, it's the 5G, but we got to break him into his two pieces. Oh, actually, 5G is going to go the other way. I'm sorry. It's going to go like this because I brought him down like that, so 5G is going to go shooting off this way. And this is going to be, he would have been way out here, but this will be 70 degrees. This is not drawn to scale by any stretch. Okay? All right, and so this will be mg, or this will be 5g cosine of 70, and this will be 5g sine of 70. So that's this guy, 5g sine of 70, and then I've got the kinetic frictional force pushing back this way. I've got the normal force going up here. So let's take a look at the sum of the forces in the y direction. Now, I didn't say anything in the problem, not being cute or anything like that, saying, oh, he's so heavy that he's crashing through the thing at the same time. No, we're not doing that. I'm not going to play that. Well, so what's the sum of the forces in the, oh, I forgot this guy. We got to put the acceleration, and I'm going to assume the acceleration is going that way, in the x direction. I'm assuming he's going this way. Okay, so the sum of the forces in the y direction are going up is the normal force minus mg, or 5g, times the cosine of 70. And that equals 0. So n equals 5g cosine of 70. And there's a method to my madness why I always start with the y direction, because especially when you're dealing with friction, that's where I get my frictional force. Because if you remember, you've seen it once in your whole life, and I erased it after 30 seconds. So you probably don't remember. We said that the frictional force, F of k, equals the mu of k times 5g cosine of 70. What we're after, you might be going, well, what are we after? We're after A. We've got to find A so that I can finish the problem. I'll find D quick enough using a little trig. I'll use the inverse sine of 15. I'll just divide 15 by the sine of 70 and get what D is. Is there something making weird noises? Okay. All right. I thought it was just my stomach growling, but it's not. All right. So now we got, now, some of the forces in the x direction. Okay, we can do this. We can do this. We've got f of x equals, well, only two guys. Oh, what are we supposed to put? 5a, right? Don't forget him, because Newton's second law, the net forces in the x direction are causing that acceleration times the mass. Okay, so we got 5a. And this will equal, the positive guy is 5g sine theta. Sine of 70 minus mu k 5g cosine 70. So I'm going to divide both sides by a, or by 5. And I get the acceleration is equal to g sine of 70 minus mu k g cosine of 70. And I forgot my calculator. Somebody have one handy? Oh, is that an 89? I don't know how to work those. Ah, there we go. Good old high school teacher, TI 84 plus. Okay, so I got 9.8 times sine of 70 minus 0.4 times 9.8 cosine of 70. That's 5.1 meters per second squared. Now that looked really hard and scary when we first started, right? Looked like, oh my gosh.
So mu of k?
Mu of k is 0.4. We decided mu of k was 0.4. Okay, so does that make sense to us? In other words, if something is being held up, sliding down, it's not sliding at 9.8 meters per second squared, right? It's going a little bit slower than gravity, quite a bit slower, just like half. Okay? That's about to drive me right out of my gourd. I don't know about it. I'm sure you all are going, man. All right. Okay. Now, so we can figure out the final velocity. I'll just tell you right now, d is equal to 15 divided by the sine of 70, because d sine of 70 equals 15. So, thank you, Rachel. What do we get?
I'm in radians, sorry.
Oh, you're in radians? Oh.
15.96.
15.96. Oh, let's call it 16. Good enough. 15.96. Let's say 16 meters. Which makes sense. 70-degree angle is pretty big. Okay, so we've got v squared. So vf squared will equal 0 squared plus 2 times 5.1 times 16. And so vf equals the square root of 10.1 times, or 10, roughly the square root of 165, we'll say. Ballpark it. 20 times 20 is 400. 13 times 13 is 169, right? So this is about 13 meters per, I'd say 12.87. It's 12.84? Oh, wow. I can still guess with the best of them. 12.8 meters per second. That's how fast it's going. Now, if it was just in free fall, it'd be quite a bit more. This would be 9.8. So it'd really be careening down there. It'd be going twice as fast, or quite a bit faster. Well, not quite twice as fast. Okay. All right, so that's the way you do friction, and that's, so let's put it all together here. Wow. There should be more to this. No, we've pretty much done it all. One thing I do want to tell you about, now let's take a look at, we're going to do the Superman problem, which I kind of liked. It's at the end of the book. It's at the end of the chapter. But first, let's look a little bit more at the normal force here. Let's look at static conditions, okay? At static conditions. Let's say I've got a block sitting on the carpet, okay? I like 5 kilograms. I don't know why. I'm just kind of stuck with 5 kilograms, okay? And I'm going to apply a force of 40 newtons to this guy at an angle of 30 degrees. So those of you who, nobody can see that, I'm applying a force of 40 newtons at an angle of 30 degrees below the horizontal, like that. Okay? Now, what I want to figure out, so I'm pushing on it at an angle. What's that going to do? If I didn't have a force there, if that 40 Newton force wasn't there, what would be the normal force for this block? If the block's just sitting there by itself, Sitting on the ground, just like my book sitting on that table. What's the normal force? Yeah, it's great. Well, it's 5G. Right. Okay. So, right. I'm very picky. So it's going down 5G. So the sum of the forces in the y direction here are equal to 0 because it's not accelerating, but I've got a normal force minus 5G. And so the normal force equals 5G. Now I got a question for you. When I push on it like this, what happens to the normal force? It should do what? Decrease or increase? If I'm pulling on it like this, N will decrease. If I'm pushing on it like this, N's going to go up. Right? Because look. Let's look at the sum of the forces. Let's look at some of the forces here. It's almost like if you want to get smacked when your wife is on a diet or something like that and she's weighing herself, you come up behind her real quiet and put your toe on the scale. That would go boing. Because basically the scale's giving you the normal force. Okay, it's taking mg, but if you add to it, anyway, they're already crazy anyway when they're dieting. But, oh, sorry, I digress. Okay, so anyway, we've got 5G going down. We got a normal force going up. So let's take a look, and so let's take a look at the free body diagram here. We've got 5G, normal force. I've got f of x going like this. I've got f of y coming down. Because I'm going to break him into his components. Here's f of x. Here's f of y. And I've also got, since he's not moving, there's got to be something holding him back. And that's the static frictional force, which would be this way. Okay? So I can figure out what that static frictional force is pushing it back. Now, an interesting problem would be, what force do I need to push with f of x to get it to move? Let's do that. Let's say I don't push on it with a force. I don't know the force. Let's say F, I don't know. What's going to get it to move? Do I need to get this to move? That's a good question. What force do I need to get this to move? Well, what I have to do is I have to overcome Fs max. I have to overcome this. So, right at the cusp of that force I got to figure out what force that is that's going to make that equal to 0. So, let's do this. It's still at 30 degrees. Okay? So, I'm going to take a look at some of my forces in the y direction. It's not flying off in the air. It's not crashing through the ground. So, Newton's second law says the net force is equal to 0. It's not accelerating. And actually, it's not accelerating in the a direction either. I'm going to find out right when I get that, what force do I need just a little bit more of, and then it'll start to accelerate. So, but that equals the normal force minus Fy minus 5G. Now notice, the normal force now equals Fy plus 5G. When I bring these guys over here, I'm going to add Fy to both sides and add 5G to both sides to the 0. And so you can see now, mathematically, why that normal force increases quite a bit. Okay? And so the normal force is equal to F sine of 30 plus 5g. Okay? And thus the frictional force, the static frictional force, is going to equal mu of s. No, we said it's carpet. Let's say mu, the static friction is 0.84 because it's carpet. Times this, F sine 30 plus 5g. Okay. Now, so I got two unknowns. I don't know this guy and I don't know that guy. So let's come up with another equation. Well, we've got this. We've got the sum of the forces in the x direction. It's also not quite accelerating. Okay? Just on the cusp. Not quite accelerating. So it equals 0. And what do we have here? We've got Fs. Oh, sorry. We've got f of x. We've got f cosine of 30 minus fs. So now I've got to stick all this in there. I've got f cosine 30 minus mu of s times f sine 30. Oh my goodness. Sine 30 plus 5g equals 0. Okay, let's do a little algebra. F cosine 30 minus mu of s f sine 30 minus mu of s 5g equals 0. I multiplied that all the way through. Okay? Now, I'm going to add mu of s 5g to both sides. I'm going to factor out my f. So I got f cosine 30, or cosine of 30. I keep putting theta in there. Minus mu of s sine 30. Gosh dang it. Equals mu of s times 5g. Because I added that to both sides. Now the force that I need to get that thing to move will be mu of s 5g divided by cosine 30 minus mu of s sine 30. Boy, is that ugly or what? That's ugly. Whew. I was kind of wanting to come up with an easy example and I made it hard. But you can follow the argument. So let's do Superman real quick. The risk of killing you all. All right, so we'll leave that up for a minute. We're just looking at all the forces in the direction. Now, here's the deal. We got Superman. Comes in. All right, we're traveling at 90 miles an hour in a car, okay? And the driver applies the brakes to his fast-moving car and skids out of control on a wet concrete horizontal road, or an icy concrete horizontal road. The car, the 2,000-kilogram car, is headed directly toward a student waiting to catch a bus on campus who is standing 58 meters down the road. Or in my case, I don't know how many students I've almost ran over here because they're texting and they're walking over to Cook Fair and they just kind of wander across Rock Hill in the middle of, like, what are you doing? Lost your mind. But anyway, but I don't hit him because fortunately Superman comes swooping down overhead and surveys the situation. Remembering from his physics class, I guess they have physics on Krypton, but anyway, that the coefficient of kinetic friction between rubber and rough, wet concrete is 0.8. He quickly determines that friction will not stop the car in time. So he flies down, exerts a constant force of 13,000 newtons on the car's hood at a downward angle of 30 degrees. Did he save the student? We'll find out. So here we go. Let's take a look at what Superman's doing here. He knows that there's friction being applied, that there's kinetic friction. Now, when you're in a skid, kinetic friction opposes the motion. I wanted to set up this problem, just if nothing else to set it up, because here's the car. Now, the car actually has a velocity going this way. But since it's slammed on its brakes, well, since Superman's staying in front of it and slowing it down, which way is the acceleration going? The other way, right. So you can still have a velocity going this way, but you can have an acceleration going that way. That's how we stop, okay? And if every time if our acceleration always followed our velocity, like I said, we'd be dropping transmissions all over the place, because as soon as you put on your brakes, your car would go the other way. So we don't do that. So the velocity's going this way, but he's got a little force of kinetic friction going this way between him and the road, okay? The mass of the car is 2,000 kilograms, and it was going 90 miles an hour, so a quick conversion, the initial velocity was 90 miles per hour. Quick conversion, take that times 0.447, that's your conversion to meters per second. You come up with about 40 meters per second. Good old Zach Greinke curveball, okay? All right, now, Superman pushes down on this thing at 30 degrees with a force of 13,000 newtons. Okay, that's at 30 degrees, so we'll break that into its two components. And, of course, we've got the mg of the car, and we got the normal force. There's our free body diagram of what's going on. What's the first thing we need to do? What are we going to break down into components here? Anything cattywampus here? Anything in an angle? Right. Superman's force. Okay? And we'll take the sum of the forces in the x direction and the sum of the forces in the y direction. Let's start with the sum of the forces in the y direction. So, we've got Superman's force. Okay, so let's get a clean board. I always start with y because that's where we're going to get our kinetic friction. Now, these are forces that are being applied to the 2,000 kilogram car. Okay? These are forces being applied to, we want to know if this is going to stop. Will D equal 58 feet? Okay, first thing we need to do, let's figure out what the acceleration is that we need. What's the deacceleration that we need? This is the way I attack the problem. I don't know how they did it. But this is, I would go, oh, then V final, I want to be 0. And so I'm going to go 0 equals 40 meters per second squared minus 2a times 58. And so I get 2a times 58 equals 1,600. And so 1,600 divided by 116, that'll be my acceleration that I need to slow down. Okay? That's going to be my deacceleration. Which in this case is actually going in the positive x direction because that's the way Superman's pushing the car. Okay? Which I don't know what that is. But I roughly worked this out ahead of time. It's roughly about 13.7 meters per second squared.
That's deceleration.
That's what's going to be required to make us come to a stop. So let's see if our overall acceleration here, now remember, so this means we've got an acceleration going this way. Let's see if we're going to find A. And if A is greater than 13.7, we save the day. Superman saved the student. Okay? Does that all make sense to us so far? Okay. Good. Now, so we got the sum of the forces in the y direction is going to equal 0. That's the second law. We're not going anywhere. And we've got the normal force minus mg minus 13,000 times the sine of 30. Sine of 30 is actually happens to be 0.5. So I know that 2,000 times 9.8 plus 6,500 equals the normal force. What I did was I just added both these guys over here. Okay, and I did the, you just eventually know that the sine of 30 is 0.5. You just know these things when you've done it for a while. Okay, and so when you do that, the normal force is equal to 26,100 newtons. Remember, the normal force is in newtons. Now, the kinetic friction then, the kinetic frictional force is equal to mu of k, which we said was what? I had 0.8? Is that what we said? That was the earlier problem. This one's 0.8. Mu of k, sorry, didn't give you all the data. Mu of k is equal to 0.8. Okay, so it would be 0.8 times 26,100. All right, so now, see, I use my y components, even though it's not accelerating anywhere, to find my frictional force. That's what it's good for. Okay. All right, now, sum of the forces in the y direction, or x direction, is equal to the mass of the car times some acceleration. It's equal to this ma, which looks like we've got, it's all positive. We've got f of k, so we've got 0.8. Well, let me write it up algebraically first. We got f of k plus 13,000 times the cosine of 30. Well, look at that. We've got all numbers. This is great. So the acceleration is going to equal 0.8 times 26,100 plus 13,000 cosine. Cosine of 30 is about 0.86. So did I do the calculations here? Well, no. It's times 13,000 cosine of 30. Okay? Divided by 2,000. And when that's all said and done, A equals, I did get this far, 16 meters per second squared. Did Superman save the person? With a lot of room to spare. Because if we put in 16 here and solve for d, for the distance, it'll be a much less. It comes out to be like 50. So by 8 meters, 24 feet, he saves the student's life. Yay. That's putting all the ideas together in Chapter 4. We didn't do any one type of problem that I will give you. Okay, we've got time to do it on Thursday. We got to look more at when I push on something and it pushes back, how that Newton's third law. We got to look at a little